Yeah, thank you for the introduction. And thanks to the organizers for having the opportunity to talk here about the very recent work in our group. Um, so this is kind of on the intersection between fracture mechanics and machine learning, if you want. So I myself, I'm not an engineer, I'm a trained mathematician. When I entered this group, I was working a lot on AI for crack detection and also for evaluating the data that we get from the DIC that Eric was introducing. So we'll talk about how, a tool that you can use basically to discover hidden knowledge or correlations in your data that you gather. And we applied this in this case for crack detection, so to actually find formulas that you can use to correct a crack deposition estimate. So this is the work with colleagues at DLR, especially Tobias, Florian, and Eric. And to set the stage, let's look again at the kind of experiments that we perform in our group. So this is a group of lifetime mechanics and the Institute of Materials Research at DLR. And what you see on the left-hand side here is a multi-scale digital image correlation test stand. This is a empty specimen of aluminium sheet that we test here. You see there are two DIC systems. So one global DIC, this is a commercial GOMARA system on the back side of the specimen. This gives us a full field DIC data, as well as the robotic, the KUKA cobot that carries an optical microscope and can be controlled. This gives us as well high resolution DIC data from the front side of the specimen. And we can match these two together in order to search for hidden information. On the right-hand side, you see an example of the high-resolution DIC. And you see already the problem. So we don't really actually know where the physical crack tip is located. And we were searching for possibilities to determine this by incorporating physics as well. What we have already is this tool that was mentioned a lot today. This is CrackPy. It's open source. You can just check it out. And especially what we need today of this is the fracture analysis part. So we have here a couple of redundant methods to calculate descriptors of the crack tip field. Of course, so the stress intensity factors, they are most important for us today. I want to focus on the Williams coefficient, so on the more deep description of the crack tip field. So this is what we will use of this. Now, what's the deal with the Williams coefficient? So you see here an example of a finite element analysis of a straight crack where we applied certain boundary conditions. These resulted in a K1 of 24 megapascal a square meter and a T-stress of -7 megapascal. And as well, you can calculate for this FE data the higher order terms of the Williams coefficients, A3, A4, and so on. They have all different units. And on the right-hand side, you see the Williams series approximation using different terms. So we start with just the A1, just the K1 if you want, or K1, K2. K2 would be the B1 then. Then we add extra terms. And as you see, the more terms I add, the better the description of the actual stress field becomes. All right, so let's go back to the original problem setup. So we want to find a good crack detection algorithm, and we want to actually start from an estimate of the corrected position and then find a correction to arrive at the real corrected position. So this is the setup. And our assumption, if you want, is that we expect there to be a formula, a function f, that takes the Williams coefficients and gives me this correction. Why do you think this is the case? There is a previous work by Ettore, this is one from 2015, where he derived this formula, this one here. A minus 1 is the first negative coefficient of the Williams series. A1 is the one that we know. And if you apply this formula iteratively for the x correction, you arrive at the corrected position. The problem is the derivation is only valid under mode 1 conditions, and you don't have a y correction. So you just have this correction parallel to the correct path. And in real DSC data, we don't really know whether we are parallel or we have an offset. So this is why we wanted to find this more general formula. Yeah, so I sat down and wanted to derive this, like basically at the paper, as the mathematicians do, right? We wanted to find this formula, but I couldn't figure it out really. So we said instead we could like try to learn it with data. So that's what we tried. And there's a nice tool that you can use to search for formulas. It's called symbolic regression. So you all know linear regression, right? You just fit a linear line to your data. This is a very restricted model, but it's very fast and very easy. If you go back from these models and just search the whole space of mathematical expressions for something that fits your data, this is an NP-hard problem. So it's very hard because of this combinatorial explosion of formulas. But there's this, sorry, this was one too far. There's this very nice modern tools. They use like deep symbolic regression. They use neural networks, recurrent neural networks, that have you suggest new formulas that you can search, that you can evaluate. And this tool that we used here, called FISO, yeah, there's the video. It even incorporates unit constraints. So you only select formulas that are physically same, where the units, they match with your expectation. So that's what we applied. Now, where does the data come from? So to train this model, we just use simulated data. So we set up an FE model, this one here, where we can now change the boundary conditions and create a data set. This, so here you see an example of this, where we just fixed one mixed mode loading condition. And now we can select a point here, and we know exactly which correction vector we have for the point, right? Because it's a simulation. And we can here fit the Williams series and calculate the Williams series coefficients at that point. Now, the only thing that we need to do is we just need to select randomly a couple of points. In this case, for each simulation, for each boundary condition, we selected 1,000 points randomly and set up a data set, yeah, where we match the Williams coefficients with the correction vector. And then, yeah, we started the FISO model, the symbolic regression model. And here are the results. So for mode, so that's just the X correction, the one that was known before for mode 1. Okay. And in case of mode 1, we actually almost exactly recover the known formula. So that's just like instead of -2, there's a minus 0.1, 1.9, sorry. And the fit is quite well. So here you see the Pareto front of formulas, and the blue one is for mode 1, so it's quite good. For the mode 2, we get a very similar formula. We basically just replace the A's by B's, so that was reassuring. And we even get one for mixed mode, so for all training with all the data points. But it actually, the fit is not quite well, so the error is quite high, so it doesn't really work for all cases, actually. For the Y correction that we wanted, this is the generalization. We have a very similar formula. So this is also newly discovered, and for mode 1 also very similar. So probably one could have guessed this, but yeah, we didn't. So. Okay, so how do the results look like? So with the formula that I highlighted, this one, I plot here for one example the correction vectors and 0 points towards the corrected position. And even for mode 1, the other one that we found here, you have a very nice convergent behavior. So we expect that we can iterate these formulas, right? We can just like iterate, and then yeah, we arrive at the corrected position. And this worked really like a charm. So for these formulas, you need about 5 iterations to actually arrive at the correct position. Yeah, so we're happy, right? But this is just an E-simulation, of course. So we trained with this data and so on. So how does it look in practice? Yeah. So let's go back to the test stand. And you see here, even like for this data that the model has never seen, so we never trained with that data. We just derived the formula with the E-simulation. Even for that one, we get a very nice corrections. As a starter, so of course, you always need a starting point. The starting point needs to be good enough so that you actually converge and don't run out. In this case, as a starting point, we use this line intercept method, which is also part of CrackPy, but you can use any other method. So if you have some other special method that you like, you can just put this correction on top. And yeah, if you're close enough, it might work. So there's another issue. So maybe I say that at the end. So let's see. Yeah. So let's summarize first, and then I do the conclusion. So what we did is we had this idea we want to come up with a formula that corrects, to find the correct position iteratively. The approach is as follows. So we started with ANSYS, with the E-simulations, used CrackPy to determine the Williams coefficients. Then we created a huge data set out of this. And then in this data set, you can use the method of your choice to search for correlations, knowledge. And in this case, we use this deep symbolic regression. All right, so to sum up, we have this corrective correction formula, which is based on Williams coefficients. We trained just with the E-simulations and developed with CrackPy. This FISO, so just maybe to say this again, we really like this method, and it might be something that you could use yourself if you think that there is a hidden information or knowledge in the data that you have, to search for correlations, to search for knowledge. We will for sure do this because we have, as Eric was saying, we have hundreds of gigabytes of data. Yeah, it will be a fun experience of one of our PhD students. Yeah, but it's a very cool method. That case worked quite well, and I'm happy with it. All right, so we published this recently in International Journal of Fatigue, if you want to check it. Otherwise, so just approach us if you are interested in the method or in physical optimal, symbolic optimization. In general, we are open for collaborations, talks, yeah, especially.